Alright, so in this section, we continue hypothesis text testing, which in this case, we cover errors in hypothesis testing. Well, first of all, let's recall that the purpose of conducting a hypothesis testing is to verify the validity of some claim about a population, but based on a single sample. Because again, keep in mind that it may not be practical, or maybe it could be even impossible to reach out the entire population. So that's what we do in Statistic: take a sample and take it from there. All right. So there are two types of errors in hypothesis testing, and these two errors arise when we run into issues with the sampling, which in some cases the sample may not be representative of the population as a whole, which and if that's the case, well, all the process is invalid, you know. So for example, let's look at type 1 error. So type 1 error is the mistake of rejecting the null hypothesis when it's actually true. That is, our HA, H1, I have H1, HA, our ha wins, but the ho was true. A real life example, well, is convicting an innocent man. Well, we have seen this very, very often times. You know how many people go to court, or they are declared the death penalty or something, but they were innocent people. And uh, what gives rise to type 1 error? Well, sampling error. Okay, let me give you an example here. So I made this grid right here, this population, so in which the claim is that less than 50% of the people has coronavirus, for example. Here I have the entire population, let's say, of a city or a community. We don't have to say the entire country. I mean, look at the size, it's pretty tiny. Let's just keep it to a community. So maybe the colors are a little bit hard to distinguish, but I have blue dots that represent the people who do not have the coronavirus, and green dots, a bunch of green dots that represent the people that have it. Okay, so well, your claim as a researcher is, well, less than 50% of the population has COVID-19, has coronavirus. Well, there could be issues here with the way we conduct the experiment. For example, what if I take this sample? If I take this sample, can you see that in this case, well, in a way, the sample you take actually, in a way, well, supports your conclusion, supports your claim, that because if you count the number of green dots, I have 1, 2, 3, 4, and 5, and mostly they were blue dots, which is the people that doesn't have it, So this sample here represents, in a way, the number of people that do not have it, right? However, well, we are not going to have access to all this information. Again, keep in mind that the sampling is random, but let's suppose that the population is distributed this way. Okay, do you see the issues here with the sampling here? Well, what if you take a sample over here? All right, what if you take a sample over here? Well, in this case, taking this sample will prove this wrong. See what I'm saying? So in this case, well, this sample is not representative of the entire population. And this one, despite, well, you look at the entire population here, we see more green dots then blue dots, which suggest that this is not true. This statement is not true. So, well, in this case, the experiment in the sampling experiment must be redesigned. Well, because in this case, I just randomly selected, boom, this sample right here or that sample there. Well, maybe take something in the middle. Well, that sample may not even be representative at all. Okay. So this is going to take us back to chapter 1, if you might remember, when we cover all the different ways or different methods to, uh, to take samples. I remember stratified sample, clustering, all these methods. Well, maybe we need to use one of those methods in order to get a better sample, a sample that is more representative. So type 1 errors are due to sampling errors like it is here. Now let's look at type 2 error. The type 2 error is the mistake of failing to reject the null hypothesis when it was actually false. When actually you had evidence indeed to prove some statement wrong. So in this case, well, what are we going to do? As an example, well, actually, the who wins, but the ha was actually true. That is, the null hypothesis wins, but actually you were correct as a researcher. What is an example? Well, letting a guilty man go free. And we have seen this many times. And well, this type of errors occur due to the fact that there is never enough evidence to accept the null hypothesis unless the entire population is sampled. But again, it's a task not easily done. It's the task not easily done. So that's why we do this. We conduct these processes of, of taking a sample. I think these pictures right here will give you a good idea of what type of error and type 1 error and type 2 error are. For example, here we have a doctor telling a man, you're pregnant, right? He's giving him a false positive. And over here for type error, look at this picture. Well, you can see the belly of the lady. Clearly she's pregnant. However, the doctor is telling her, no, you're not pregnant. What is she giving her? A false negative. So that's what you could, how you can relate these type of errors. So if we go back to the previous examples on the previous sections, well, in this case, we for the first example 1, we had we reject the null hypothesis because there was enough evidence to support it. In other words, HA wins. So the possible, in this case, possible type of error is type 1 error. Not that there is an error, but there could be an error. What about the second example? We failed to reject the null hypothesis. So in this case, because we failed to reject the null hypothesis, HO wins, which is possible type 2 error. On the third example, we got again, we had enough evidence to reject the null hypothesis. That means that HA wins, possible type 1 error. All right. So now that we know a little bit more of hypothesis testing, well, I mean, you look at the process, and if you will, it's kind of straightforward process. Even though it takes a few steps, stating, uh, understanding what the type of information that we have available, and also determine whether the test is a two-tailed or single-tailed, and then state the how and state the how. This and the hypothesis, the null hypothesis, and the alternative hypothesis. All right, so now we're gonna move on to to the next topic. So on the previous video, we tested claims about population proportion. So now we are going to test a claim about a mean in which sigma is known. But what is sigma? Sigma is the population standard deviation. So this test is typically a strong test because at least we know one parameter of the population. Well, we know a statistic, Again, keep in mind the difference between a parameter and statistic. A parameter, it's a numerical value that comes from the sample, as opposed to a statistic, which comes from which comes from the population. So it's stronger when we know something from the population, because that's ultimately what we want to do some inference of. All right. So now let's see. The next topic, well, for this topic, testing a claim about the mean, not the proportion, well, we need to take a couple of assumptions. Well, the sample is a simple random sample, and either of these two conditions is satisfied. Number one, either they're telling us that the population is normally distributed, or the sample size is greater than 30. Could be people or elements, simply elements. Now, well, the test statistic, how are we going to calculate the test statistic? Well, the process will be very similar from the previous section. Well, this was a formula to find the test statistic. Now, the test statistic to make inferences about the mean, in which sigma, the standard deviation from the population, is known. Well, we are going to use this formula, and the criteria is exactly the same. Reject if our test statistic falls within the critical region, within the shaded, and fail to reject if it doesn't fall within the shaded region. That's what we mean by critical region, if you will. All right, let's look at an example. So, a company claims that the average time a customer waits on hold is less than 5 minutes. Well, in this case, they're not telling us less than or equal or at most, so it's telling us less than. What is this going to tell us? That's going to be the alternative hypothesis. So we can start by that. Well, let's finish reading the problem. Well, a sample of 35 customers has an average waiting time of 4.78 minutes. Well, that's a good number. Sounds good, but is the sample representative? Well, we will figure it out. Assume the population standard deviation for wait timing is 1.8 minutes. Test the company claim at alpha equals 0.05 significance level, which is 5%. So that means that we are going to find the C-score related to What was that? Give me a second. Stick to my colors. That's going to be 95. Okay, that's a 95% over here. And in this case, well, less than. Now let's get the information again. This is the population. We are going to take a sample. All right. So begin the population. We don't know and we don't care. The mean, mu, is 5 minutes. You know? The standard deviation of the population is 1.8. We are going to take a sample from here. Take a sample. Okay, a sample of n equals 35, and in this case, the x bar, the mean of the sample, is 4.78 minutes. Okay, so let's enclose our sample. Okay, so population sample. Well, maybe we can think of the standard deviation of the sample, but that's not relevant. So we're not going to care about that. All right. Well, so I mean, look at the problem. Well, what the company claims is that the average waiting time is less than 5 minutes. Well, so they conduct some experiments, I don't know, maybe in the form of monitoring the call or monitoring certain number of calls. I mean, a sample of 35, that's not all the calls. That's only 35 of the calls. And the average waiting time is 4.78. All right. So, well, maybe, well, we're done because 4.78 is less than 5. But I mean, yes, those, you can compare the numbers and clearly that's less than that. But we need statistical evidence to support, and also that statistical evidence is with the precision of 95% precision or alpha 0.05 significant level, which is basically the same. All right, so let's take the null and the alternative hypothesis, that is the ho and the ha. Okay, so well, the researcher, that is the company people, said they're claiming that the mean is less than 5. Again, recall that the alternative hypothesis never ever has the equal symbol. Now the null hypothesis will be the logical opposite of this statement. Okay, what is the logical opposite of mu less than 5? That is correct if you were thinking that mu greater than or equal to 5. Okay. All right, so in this case, is this going to be a two-tailed or a one-tailed test? Well, in this case, we're going to have a one-tailed test. Now, look at the direction of the inequality symbol of the alternative hypothesis. Is pointing towards the left. So it's going to be a left-tailed test, a one-tailed test, in particular towards the left. So that means this alpha of 0.05 is going to be sent over here. Okay, so I'm going to find a critical value related to alpha 0.05. And when we get that by using our graphing calculator, inv norm of 0.05. And again, on your calculator, you will see this 0 and this 1. Okay, so I'm going to show you again how to get that. So we're going to go to second dister. or the vars one, and we are going to hit in norm. We want 0.05 of the area. This 0 and this 1, you can just ignore it again. Click enter, or even if you have the inv norm operator without this 1, this comma, and this 0, it still works. So negative 1.64. Again, keep in mind that the rounding rule for z-scores is 2 decimal places. So negative 1.64. Okay. Negative 1.64. So we are going to calculate the test statistic using the formula that we got from the previous page. And I'm going to write again. If our test statistic falls within this region, that is, we get a number that is greater than negative 1.64, then we fail to reject. And despite this 0.78 being smaller than 5, well, this doesn't prove anything. This is not going to prove anything. Maybe our sample was not representative, so we need to do something else. All right, we need to obtain newer data. Otherwise, if our test statistic is a number that is less, a lot less, or just slightly less than this cutoff value stated by the C critical, negative 1.64, then we have enough evidence to support our claim in accordance to our data. All right, so the formula to calculate the statistic is the mean from the sample minus the mean from the population divided by sigma, which is the standard deviation of the population, divided by the square root of the sample size. Okay, I would like, if you want to memorize these formulas or something, well, keep in mind that we always subtract the mean from the population from that of the sample. In the previous topic, see how we did the same? We subtracted the proportion from the population from that of the sample. So we follow the same order. All right, we follow the same order. This is from the sample, and that one is from the population. Okay, let's put numbers to this. So, well, this is going to be x bar from the sample, okay, which is 4.78 minus mu from the population, whatever is claimed, which is 5, divided by the standard deviation of the sample, which is 1.8, divided by the square root of n, which is 35. Well, in this case, notice I just started plugging in numbers without verifying that the conditions to perform this test are met. Let's check if they are. All right. So, number 1, the sample size is greater than 30, so that gives us green light to perform the test. Otherwise, if the sample size were smaller than 35, well, then the problem must state that the population is normally distributed. In some other cases, in some other examples, they're going to state both of them. Okay? So in this case, we're good. Now, how do we type this in the graphing calculator? Well, I get number 1, negative 0.72. Let me show you how to put this in the calculator. So first, I'm gonna type this difference in the numerator, but be sure to open parentheses. 4.78 minus 5, close parentheses, and then divide by, I would open parentheses again, 1.8 divided by the square root of 35. I'm going to move on here and close parentheses for the denominator. Having this parentheses prior to the 0.78 and after the number 5 ensures that whatever you put in the division affects the difference and not just one of them. Okay, so that's what I get. Keep in mind the rounding rule is 2 decimal places for z-scores. So 0.72 is our test statistic here. All right, that's our test statistic. Let me put it in a circle, and it's time to compare. It's time to determine whether we have enough evidence. We have sufficient evidence to determine whether our claim is true or not. And it turns out that in this case, negative 0.72 is going to fall in the unshaded region. What does that mean? Again, anywhere here reject, anywhere else fail to reject, the null hypothesis. So in this case, unfortunately, well, even if this number is lower than 5 minutes, is lower than 5 minutes, well, statistically, we don't have evidence to support this claim. So we fail to reject the null hypothesis. There is not enough evidence to support it. Now we're going to use the p-value method and compare with the significance level. So in this case, we're going to use the normal CDF. So we're going to find the probability, in other words, the area under the curve that goes from negative big to negative 0.72. All right. And well, again, you're gonna have the 0 and the 1. If you do that, you may not type, and the calculator is still gonna work. So I'm gonna go to stat. No, not stat. I'm gonna go to second vars to get the distributions and normal CDF. So I'm gonna use a negative big number and then negative 0.72. The 0 and the 1, keep them, and I'm gonna get that value. Otherwise, if you erase this 0 and this 1, that doesn't have any effect. You get the same. So I get 0.236. P-values are rounded to 3 decimal places. Z-scores are rounded to 2 decimal places. All right, so I'm going to put the p-value versus alpha and see which one is bigger. So in this case, p is 0.236. But alpha, what was alpha? 0.05. In this case, clearly this is bigger than. So in this case, this area right here is way bigger than the one dictated by this cutoff value. Because this area is bigger, well, that means the probability of failing to reject the null hypothesis is bigger than otherwise. So that's how we do this using the p-value method. So in this case, fail to reject, and you should get fail to reject. Well, so in this case, this means that HO wins, which suggests a possible type of error too. So what could be the solution here? Well, so in this case, it's not a sampling error, as we discussed in the previous example, with the COVID example, because in this case, we got type 2 error. Again, keep in mind that the type 2 error relies on the fact that there is never enough evidence unless we survey the entire population. So what can we do here? Maybe number one, increase the sample size, or otherwise simply monitor every single call, not just a sample of 35 calls. That's if, as a company, as a CEO, for example, I want to show this as compelling. Okay? All right, let's do another example. So a company claims that its laptop batteries average more than 35 hours of use per charge. Okay, more than 3.5 hours. Okay, that more than, not more than or equal. Well, that's going to tell us that's the alternative hypothesis. All right, so a sample of 45 batteries lasts an average of 3.72 hours. Well, that's more than 3.5 hours. But again, did you see what happened in the previous example? Having more than what is claimed or less than what is claimed doesn't prove anything. We need to have compelling statistical evidence in order to support our claim. And that's what we are going to do here. All right. So assume that the population standard deviation is 0.7 hours. That's the company's claim at 0.1 significance level. That means, well, this is going to be somewhat 90%. It's going to be a less precise test, but still, 90%, depending on how strict quality controls we want to undergo. So 0.1, 0.10. All right, so conditions for this test to be able to be conducted. Well, the sample size clearly is greater than 30. So it doesn't matter if the population is normally distributed. In this case, we're good. All right, so now let's see what are we going to do. Population size, big N, I don't care, we don't care. We don't know and we don't care. The mean of the sample, the mean of the sample is, no, not the mean of the sample, the mean hours of per charge, that's 3.5. The mean and the standard deviation is 0.7. All right. Now let's see what we're going to do. We are going to take a sample in which little n is 45 and the mean of the sample, x bar, is 3.5. That's our sample. Okay, so let's state our ho and our ha. The ho, which is the null hypothesis, and the ha, which is the alternative hypothesis. Well, in this case is the alternative hypothesis is given in the sentence at the beginning of the exercise, in which the mean is greater than 3.5. All right. So the logical opposite of this statement is mu less than or equal 3.5. All right, so let's see. Let's find the critical value. Now, before finding the critical value, we are going to determine whether this test will be one-tailed or two-tailed. So, in this case, well, look at the inequality sign of the statement on the alternative hypothesis is an inequality sign and it's pointing towards the right. So it's going to be a one-tailed test. So let's see. It's going to go in this direction. It's going to go over here. And we're going to find our cutoff value. That's going to divide the rejection region from the not rejection region. Anything that falls within this region, reject. The null hypothesis. Otherwise, fail to reject the null hypothesis. So if our statistic value falls here, well, we lose the argument, or we don't have compelling evidence to show that this is true. Otherwise, if our statistic value falls in here, well, then we have compelling evidence. Okay? All right, calculate the critical value. So, inv norm of, in this case, well, we're going to find inv norm of, well, you could, okay, this is the tricky part sometimes. Number one, you could do the inv norm of 0.1. All right. Whoops. That's going to give us a negative z-score. However, keep in mind that the Gaussian curve is symmetric. So if you do the inv norm of alpha, well, just change the sign. If you don't feel comfortable doing that, well, change this 90% to decimal and do inv norm of that number. In this case, inv norm 0.9. You should get the same number, but now positive. Either way is fine. So in this case, the z critical is 1.28. All right. Now, let's see. So inv norm of 0.90 equals 1.28. Let's calculate our test statistic. Z equals sample minus population's mean divided by the standard deviation over the square root of the sample size. Putting numbers to this is 3.72 minus 3.5 divided by 0.7 divided by the square root of 45. Using a calculator, I get 2.11. Okay, this is time for judgment. So in this case, is 2.11 falling in the rejection region or the non-rejection region? So in this case, clearly 2.11 is larger than 1.28, falls here. Anywhere representatively. So we reject the null hypothesis. That means the computer company has compelling data to claim that their laptop batteries last more than 3.5 hours. All right. Now let's do this the p-value method. Normal CDF. Now in this case, notice that this 2.11 goes from here all the way to something big, to infinity, if you will. So 2.11 to big. And again, when you type it on the calculator, you're going to end up with this 0 and this 1, which again, you can delete them. Now you can delete those numbers. So normal CDF, well, let me do that again. A second dister, normal CDF, that's a 2.11, and just something big, 0 and 1, I get 0.017, which in this case, that's our P. Now let's compare it with alpha. Our alpha, keep in mind, that is 0.10, and in this case, it is the case that P is less than or equal. When the p-value is less than or equal the significance level, then we reject. Happy face for reject, sad face for failing to reject. So we reject. HO, there is enough evidence to support it. But well, what if the sampling of these laptops was not done accordingly? Well, then we have a type 1 error. But I mean, that's the what if. Every time we conduct a hypothesis test, keep in mind that we are not necessarily making the mistake. I mean, the numbers are there. How they were obtained, well, we don't know. We don't have access to that type of information. That's why we introduce this additional analysis. Type 1 error, type 2 error. Possible type 1 error, possible type 2 error. All right, let's look at another example. Let's look at our third example, in which, well, what do we have? A researcher is testing the claim that the average adult consumes 1.7 cups of coffee per day. Assume that the population standard deviation is 0.5 cups per day. A sample of 30 adults average 1.85 cups of coffee per day. Test the researchers claim at alpha 0.05 significance level. All right, well, number one, be very, very careful. What did we say about the alternative hypothesis? What did we say about it? What did we say about the alternative hypothesis? Never has the equal sign. It's always greater than a number, less than a number, or not equal to whatever number. Now, in this case, be very, very careful. Why? Look at the wording in this case. Let me highlight the first sentence. All right, let me highlight this. This sentence, in this case, careful when reading these problems, because this is not the researchers' hypothesis or claim. He's not, okay, here in this case, the researcher is not claiming that the adult consumes. In this case, they're telling us that the researcher is testing someone else's claim. Okay, be very careful when reading this type of sentences. Okay, let me repeat that again. This is not the researcher's claim. This is a researcher testing the claim that someone else said, not him, someone else. Okay, so this is going to be very, very important when stating the null hypothesis and the alternative hypothesis. Okay, so in this case, well, so It's possible that the researcher read this on the newspaper or on Twitter, or someone shared a meme, on social media, or he was driving, he was on his way to work, and he heard that on the news, all right? And then he is like, no, I don't think so. I'm going to prove this guy's wrong. I'm going to make my sample, I'm going to make my research, and, and I'm going to get statistical data to either prove this wrong or prove this false. All right? So let's see. Okay. So in this case, let me write something else. This is what a researcher wants to prove wrong. Okay, so well, now let's get the rest of the data. Well, we are assuming the population standard deviation is 0.5 cups per day. A sample of 30 adults average 1.85 cups of coffee per day. And test the researchers' claim at alpha 0.05 significance level. All right, we are going to do the usual population size. We don't know, we don't care either. We're not going to reach out the entire population. The mean of the population is 1.7, which is what is to prove wrong, and the standard deviation of the population, which is 0.5. And well, like I said, we don't care how big the population is. All we do is take a sample of n equals 30 coffee drinkers with a mean of 1.85. All right. Now, state the null and alternative hypothesis. That's going to be the tricky part, maybe. The ho and the ha. Okay, what's the null hypothesis? What's the alternative hypothesis? So what are we reading in the main claim? Do we have something greater than, less than? Well, in this case, okay, the adult consumes 1.7. This is telling me that the null hypothesis should be read, should be stated as the mean number of coffee cups to be mu equal to 1.7. Okay, so that's whatever claim the researcher read that is to be proved wrong. So he's gonna see, he's like, no, that's not. And we're gonna do some statistic to prove whoever said that is wrong. All right. So we have alpha 0.05. That means we are going to conduct a 95% precision test. Okay. So in this case, well, because of this, look at that, it's a not equal. Not equal. That means we split this into two regions evenly. That means alpha over 2 equals half of this number, 0.025. Alpha over 2 equals 0.025. That's the area. That's the area that we shade. All right. Split it evenly. Split it evenly. Well, we are going to have a cutoff value on either side. Anything that falls within this region, you know the drill. Fail to reject. the null hypothesis. Reject otherwise reject the null hypothesis if we fall within the shaded region. Alright, so time to find critical values. Critical values for alpha 0.025. Okay, second, this term in norm 0.02501. Negative 1.9599, well, that rounds up to 1.96. Negative 1.96. 1.96 by symmetry. Again, you don't have to do the other one. If you want, however, well, it's up to you. Okay, but take advantage of the symmetric property of the Gaussian curve to get the right values here. All right, find the critical value. Let me write it down. So in norm of 0.02501. Okay, we already did it. Negative 1.96. Well, plus minus. All right, it's okay to just find one. Okay, calculate the test statistic using the formula sample minus population's mean divided by the quotient of the standard deviation and the square root of the sample. Putting numbers to this, well, 1.85, 0.5 over the square root of 30. Okay, if I do this in the calculator, I'm going to get 1.64. Ooh, what's going to happen here? 1.64 falls in the unshaded region. So here it turned out that the researcher thought he would have the nerve to prove whatever he read that was wrong. Well, the problem here is, well, he didn't get enough evidence to support the claim that whatever he heard on the radio or read on the news was wrong. Okay, so in this case, we fail, epic fail, to reject the null hypothesis. There is not enough evidence to support it. So let's do it the p-value way. Normal CDF of, in this case, I'm going to say 1.64 and big. Again, put the 0 and the 1, or do not put it, it's fine. Okay, so we are essentially finding the area. We are going to basically find that the area enclosed from the cutoff of our test statistic to infinity is way bigger than that of our critical standardized one, and that's how we show our epic fail here. So in this case, well, let's see. Normal CDF, second dister normal CDF 1.64 comma, oops, no, not the comma, delete, big, enter. 0.0505, 0.051, 0.051. Okay, this is P. What was alpha? Alpha was 0.05. See how tiny was the difference? We were almost there. We almost had enough evidence to support or to prove whatever was claimed as a false statement. But in this case, unfortunately, we don't have enough. We don't have no sufficient evidence to support that otherwise. Well, possibly this is type 2. What can we do? Well, maybe survey the entire population about how many cups of coffee do they get per day. Alright, and this is what we're going to do in the next example. The next example is exactly the same thing. However, now we are taking a sample size of 60 adults. Well, I'm going to do everything again. Well, I don't want to just go straight to the calculation. Begin, which is the population size. We don't care. We don't know. We don't care. The mean is 1.7. The standard deviation is 0.5. So n, which is now 60, the same standard deviation, oh no, the x bar, which was 1.85. Okay, 1.85. So same thing here, 95%, two-tailed, z-critical, z-criticals, they are the same. All right. Alpha 0.05 is being split in 2 to alpha over 2 equals to 0.025. Alpha over 2 equals 0.025. Okay, whatever falls within this region is going to fail to reject the null hypothesis. Whatever falls within this region is enough evidence to support, to actually prove that wrong. Okay, null and alternative hypothesis, the ho and the ha are the same. So mu equals 1.7, mu equals, or actually not equals to 1.7. Okay, this suggests two-tailed. The critical value in norm, blah, blah, blah. Okay, I'm just writing the same. The only thing that is going to change is the statistic calculation. Okay. So, what are we going to do next? Well, calculate the statistic. Z equals sample minus population divided by sigma over square root of n. Putting numbers, 1.85 minus 1.7 divided by 0.5 over the square root of 60 this time. That's what changes, the sample size. And I get a better number, 2.32. And clearly, 2.32 falls within the shaded region because it's bigger than the critical value of 1.96. All right. What is our conclusion then? Well, so in this case, we reject the null hypothesis because there is now enough evidence to support it. So, do you see the difference here? How we can modify our experiments slightly, you know, in a way that we can, well, not necessarily manipulate our results, because ultimately we are, by our ethic codes, we're subject to follow the rules of experiments. However, what we can just modify is sample size, the parameter that are free, for which we have the freedom to modify. Okay, in order to have better and compelling evidence to reject whatever was said by someone. All right, normal CDF 2.32 to something huge, big, whatever it is, and in this case I get 0.010. That's our p-value, and alpha was in this case 0.05. If we put them together, clearly this is less than or equal. This is less than or equal. So that's why we reject null hypothesis. All right, so this is a good place to quit. I'll see you in the next video.